Welcome to G-Fun Facts Online. Today we're talking about a biological paradox. What if I told you that the hardest, most durable substance in your entire body has a critical flaw? It can't heal itself, not even a little bit. I'm talking about your tooth enamel. This incredible, resilient outer layer of our teeth is tougher than bone. It's engineered to withstand decades of grinding, chomping, and chewing. But every day, it faces an invisible assault. The acid from your morning coffee, that afternoon soda, or even healthy fruits and vegetables slowly wears it away. This process, called demineralization, creates microscopic weak spots. Over time, these spots can become cavities, lead to painful sensitivity, and eventually, tooth loss. For the last 70 years, our main line of defense has been fluoride. And fluoride is a champion. It works by attracting calcium and phosphate from your saliva to patch up these weak spots, forming a more acid-resistant surface. Think of your enamel as a beautiful marble statue, and acid as a constant corrosive rain. Fluoride is like a really good raincoat. It protects the surface, but it can't rebuild the marble that has already been etched away. The fundamental problem remains. Once enamel is gone, your body can't make more. But what if it could? What if we could give our bodies the tools to not just patch the damage, but to truly regenerate it? That's not science fiction anymore. Groundbreaking research has unveiled a new, and perhaps unlikely, hero in the fight for dental health. It's a material you're intimately familiar with. It's in your hair, your fingernails, and the wool in your sweater. The future of dentistry might just lie in a protein called keratin. To understand why this is such a big deal, we first need to appreciate what tooth enamel truly is. It's a masterpiece of natural engineering. About 96% of it is made of inorganic minerals, mostly in the form of incredibly dense, organized crystals called hydroxyapatite. The other 4% is water and a crucial organic matrix. This organic part is tiny, but it's the secret to enamel's strength. During tooth development, when your teeth are still forming in your jaw, specialized cells called ameloblasts create a protein scaffold. The most important of these proteins is called amelogenin. Imagine building a skyscraper. The hydroxyapatite crystals are like the concrete, but you can't just pour concrete and hope for the best. You need a steel framework, a scaffold, to guide the concrete into the right shape and give the building its structural integrity. Amelogenin is that scaffold. It directs the growth and alignment of the hydroxyapatite crystals, arranging them into the tightly packed, interwoven structure that gives enamel its legendary hardness. Here's the catch. Once a tooth erupts through your gums, those specialist cells, the ameloblasts, are gone forever. The construction crew leaves the site. This means if the skyscraper's facade gets damaged, there's no one left to rebuild it. This is the central challenge of modern dentistry. We can drill out decay and fill the hole with resins or ceramics, but we're just patching the structure. We're not healing it. Fluoride helps remineralize the surface, but it can't rebuild the complex, three-dimensional architecture that has been lost. This is where biomimetic approaches come in. Biomimetic simply means mimicking nature. Scientists began to ask, if we can't get the original construction crew back, can we at least find their blueprints? Or maybe find a new material that can act like the original scaffold? This brings us back to keratin. A team of scientists at King's College London, publishing in the journal Advanced Healthcare Materials, decided to test this fibrous protein, known for its strength in hair and wool, for a completely new purpose. They wanted to see if it could act as a substitute scaffold for enamel repair. What they found was remarkable. The process they discovered is a beautiful example of biomimetic mineralization. Here's how it works, step by step. First, they applied a solution containing keratin, which was extracted from wool, to a section of a tooth with early-stage enamel damage. The keratin proteins didn't just sit there. They began to self-assemble directly on the tooth's surface. They formed a highly organized crystal-like scaffold. This process is helped by disulfide bridges, which are strong chemical bonds that give keratin its stability and structure. Think of it like bringing a new, prefabricated scaffolding system to the damaged skyscraper and having it automatically click into place. The second step is mineral attraction. This newly formed keratin scaffold acts like a powerful magnet. It starts pulling in the calcium and phosphate ions that are naturally present in our saliva. Your mouth is already a rich soup of all the building blocks needed to create enamel. But without a guide, they just float around. The keratin scaffold provides that guide. This leads to the third and most crucial step, guided crystal growth. The keratin template doesn't just attract the minerals randomly. Its unique, flexible structure guides the organization of these minerals. It tells them exactly where to go and how to align, encouraging them to form new hydroxyapatite crystals that mimic the precise, interwoven structure of natural, healthy enamel. It's not just dumping concrete into a hole, it's carefully pouring it into a perfectly designed framework to ensure the repair is just as strong as the original structure. The final result, which happens over time, is the formation of a brand new, dense, mineralized layer. This layer isn't just sitting on top of the tooth. It's fully integrated with the underlying tooth structure. It effectively repairs the early enamel defects. And the benefits go beyond just filling the lesion. This new layer also seals the tiny, microscopic channels in the underlying dentin layer. These channels are what cause tooth sensitivity because they lead directly to the nerve. By sealing them, this keratin-based treatment could potentially eliminate that sharp pain you get from cold drinks or sweet foods. When the researchers tested this new keratin-induced layer in the lab, they found it was significantly harder and more durable than the conventional plastic resins that dentists currently use for fillings and dental restorations. One of the most exciting aspects of this research is its sustainability. The keratin used in the initial studies was sourced from wool, which is a readily available and renewable resource. But the researchers point out that it could also be sourced from other biological waste materials, including human hair from salons. This aligns perfectly with the principles of a circular economy, where we turn waste products into valuable new materials. This is a massive advantage over many materials used in dentistry today. Things like plastic-based composite resins are derived from petrochemicals. They are not biodegradable, and they can wear down over time, requiring replacement. A keratin-based solution is not only more sustainable, but it's also inherently biocompatible. Keratin is a natural protein that our body already produces. This means it's extremely unlikely to cause adverse reactions. It's well tolerated by the body, reducing the risk of inflammation or rejection that can sometimes occur with synthetic materials. Plus, because it regenerates enamel in a way that mimics the natural structure, the repaired area can match the color and translucency of the natural tooth much more closely, offering a more aesthetic solution. Now, before you run out and start looking for a keratin toothpaste, it's important to manage expectations. This technology, while incredibly promising, is still in its early stages. The King's College London study has generated a huge amount of excitement, but it's a proof of concept. The next step is to translate this laboratory success into real-world clinical applications. The researchers are currently exploring what these products might look like. They envision things like a daily-use toothpaste or mouthwash that contains keratin to provide continuous repair, or a more concentrated gel that a dentist could apply professionally to treat more significant areas of early decay. They project that these products could potentially be available to the public within the next 2 to 3 years. However, this timeline is entirely dependent on the results of rigorous clinical trials. At present, the specific details about these trials, such as their current phase or status, haven't been made public. Clinical trials are absolutely essential to confirm the long-term safety and efficacy of this approach. It's one thing for it to work in a controlled lab environment. It's another for it to hold up inside the human mouth, with all its temperature fluctuations, mechanical stresses, and bacterial challenges. Experts not directly involved in the study have expressed what they call cautious optimism, emphasizing that this thorough clinical validation is the critical next step. It's also worth noting that keratin is not the only natural contender in the race to regenerate tooth enamel. This research is part of a broader movement in dentistry towards these biomimetic and regenerative solutions. For example, some scientists are working with something called amylogenin-derived peptides. Remember amylogenin, the original scaffolding protein from our tooth development? This approach uses very short chains of amino acids, peptides, that are derived from that original protein. The idea is that these peptides remember how to build enamel and can guide remineralization in a similar way to keratin. Some studies have even combined these peptides with chitosan, a natural polymer from crustacean shells, to create a hydrogel that can be applied to teeth. Then there's hydroxyapatite toothpaste, which is already available on the market. This offers a more direct approach. Since enamel is mostly hydroxyapatite, the idea is to simply deliver the finished building blocks directly to the tooth to patch up microscopic fissures. Think of it like a road crew, using a pre-mixed asphalt patch to fill a pothole. It's effective for surface-level repair and can reduce sensitivity. However, many scientists argue that this is more about patching than true regeneration. The keratin and peptide approaches are different. They're about rebuilding the fundamental scaffold first, ensuring that the new mineral structure is as organized and resilient as the original. The ultimate goal in this field is to create smart biomaterials. Imagine a filling that can respond to its environment. When it detects an increase in acid in your mouth, it could automatically release more calcium and phosphate ions to actively fight off the demineralization as it happens. We are moving from a passive drill-and-fill model of dentistry to an active biological one that promotes the natural healing processes of the tooth. Of course, there are still challenges to overcome. The long-term durability of these regenerated enamel layers needs to be proven. How will a keratin-repaired tooth hold up after 10,000 coffees and 5 years of daily grinding? The cost and accessibility of these new technologies will also be crucial. A revolutionary treatment isn't much good if no one can afford it. But the potential benefits are undeniable. The ability to heal a cavity before it even truly forms, to erase tooth sensitivity, and to restore our teeth using a natural, sustainable, and biocompatible material could fundamentally transform both preventative and restorative dentistry. The journey from the laboratory to your dental chair is a meticulous and lengthy one, but the science of keratin for enamel repair has laid a powerful foundation for a new chapter in dental health. As research continues and clinical trials get underway, we may be on the verge of a simple yet profound shift in how we care for our smiles. The promise of a truly natural solution to one of our most common health issues is a development worth smiling about, proving that sometimes the most advanced solutions have been hiding in plain sight all along.